So today we have Professor Shu from Brown University going to talk about discontinuous GAlerkin F1 for hyperbolic equation with delta singularities.
Okay, thank you very much. So I'm very happy to come here to talk about a numerical method. So what I'll try to do is that to describe the most general way so that the background, not assuming that anything is known before. So here is an outline. So I will first give an introduction to this method for solving hyperbolic equations, then describe why this appearance of delta singularities would cause additional difficulties and how to deal with it. Then an important component of the difficulty here, which can be overcome, is because there is this high order accuracy bound preserving limiter, and we will spend some time describing this limiter, which is useful not only in this context, but also in other contexts. And then finally, some applications. Okay. So let's see. So here is the conservation law we are talking about. So u here could be a vector or scalar. In the simplest case, u is just a scalar, and f of u is just a scalar function. So here, sub x is the derivative. So this is a one-dimension, 1D in space, 1D in time, one-dimensional. You can have 2-dimension, you can have 3-dimension, or even higher. But most of the applications would be in 2 and 3 dimensions. And u here, in most applications, would be a vector. So if u is a vector, you would require that f prime of u is diagonalizable with real eigenvalues. The difficulty of this PDE in terms of solving it numerically is that the solution u would have to be considered to be discontinuous. So this is generic. You cannot really assume it is smooth regardless of how you put the initial condition. So if you put a smooth initial condition, for a short time you may have smooth solutions, but for longer time you would still have discontinuities. And then because of these discontinuous solutions, you have to consider weak solutions, which is not unique. So you have to put an extra condition, which is so-called entropy condition in physics, to single out a unique weak solution that is physically relevant. So these are the difficulties which will, your schemes would have to address. So, okay, so let's look at the method. So this discontinuous GAlerkin method is a finite element method, but if you're not familiar with finite elements, so basically what you do is that you have this PDE here. You multiply it by a test function v. For the time being, you just think about v to be arbitrary C1 function. And then you multiply, of course, it's still 0. You integrate it over a cell. You cut the computational domain into individual cells. You integrate it over one cell. And you integrate it by parts, the second term. So if you integrate it by parts, you generate these two interface terms. So these two terms are sitting on the boundary between two cells. So this is, of course, still an identity satisfied by the exact solution of 1 multiplied by an arbitrary test function v. So this is an identity. So the idea is to convert this identity into a scheme, into a computationally implementable method. So what you do is that here I abuse notation a little bit. I still use u, but now I consider u to be not the exact solution of the PDE as before, but u is something in this finite element space, which is just, in words, it's just the collection of piecewise polynomials of degree k. So it is a polynomial in every interval I sub j, and which may be discontinuous across cell boundaries. So if you consider u to be in this space, and then you consider the test function v also to be in this space, then the previous equality would have some problem, because if u and v are both in that space, which is piecewise polynomial, collection of piecewise polynomials, then these guys do not make unique sense, because at j plus half, the function u and the function v are both double valued. It has a left limit, it has a right limit. So you have to determine how you are going to treat these ambiguities. And that is how discontinuous GAlerkin methods go into play. So you design these treatment of these things in the correct way, you would end up with a good method. So for hyperbolic problems, the treatment of this ambiguity u of j plus half is the following. You replace f of uj plus half, which is not well defined, by f hat, which is a function of two variables rather than one. It depends on both the left limit and the right limit, and it satisfies these three conditions. So it's consistent. In other words, if you don't have jump, then you should return fu. The most important thing is that for scalar case, the most important thing is that it's an increasing function in the first argument and decreasing function of the second argument. So that's the most important thing. And then f hat is Lipschitz. The test function v, on the other hand, is simply treated as taking the values from inside the cell ij. So on the right, you take it from the left. On the left, you take it from the right. So when you do this, you end up equality 1 becomes equality 2. In other words, you want to find the function u in this finite element space Vh such that this equality holds for every test function v in the same finite element space. So here, all the terms are well defined. These integrals are well defined. So everything is well defined here. And you can show that there is a unique u in the space Vh which would satisfy this for every test function v. Now, in order to go to the computer, to implement this thing, you would have to take a basis function of Vh. It's finite dimensional, so you take a collection of finitely many basis functions. Then you write u in terms of a linear combination of these basis functions. You solve for those coefficients. So you write down explicit formulas for updating those coefficients. Then that is your scheme. That is the scheme that you go to the computer to implement. In particular, for the simplest k equals 0 case, which means piecewise constant, then the scheme degenerates to this. This is the well-known first-order monotone scheme, which has a lot of good mathematical properties. For example, it is stable, satisfies maximum principle, its total variation diminishing, it is convergent, convergence rate is at least 1/2 order, and so on. So every nice thing you can talk about, you have it for this scheme. Of course, the only drawback is that this scheme is a low-order accurate. It's only first-order because you take piecewise constant. In other words, it's not very efficient. So if you want to get enough resolution, enough accuracy, you would have to put a lot of cells. So that would mean that in multi-dimensions, at least, it will be very demanding on computational resource. So the idea is that you want to increase this k here to make the method more efficient. But at least the discontinuous GAlerkin method in the simplest k equals 0 case is this well-known and well-behaved scheme. Okay, so this is talking about discretization in space. Now in time, you would basically do the following. You discretize the ODE. So this LU is the spatial DG operator I just described. Then you have this ordinary differential equation system, which you discretize in time. For example, by this Roach-Coulthard method, explicit Roach-Coulthard method. You could also discretize this ODE by another method of your choice. Okay, so this is basically the description of the method. So it's a very brief description, but basically you understand what is going on. What you are doing is that you have picked a function space which is finite dimensional that computers can handle, which contains polynomials, piecewise polynomials of degree up to k, and then you have defined a methodology to find a unique function u in that space, which is somehow an approximation to your PDE. Okay, so now let's go to the issue of this talk, namely the appearance of data functions. Now, the data function could appear for a hyperbolic problem. The data function could appear in the initial condition. For example, you can put in the data function in the initial condition. You can put data functions on the right-hand side source term. For example, when you define Green's functions, this data function is sitting here. Or in some nonlinear cases, you could even have data functions in U with nothing here and nothing here. So here it is smooth, here it is also smooth, but just the solution becomes singular in finite time. The singular is not in the sense of the usual discontinuity, but in the sense of generating a data function. Later, we will give examples of systems which could do that. For example, pressureless Euler equations would do that. So in this kind of situations, you would have to deal with data functions numerically. Notice that the data function is not something which is easy to be dealt with numerically because it's a mathematical definition. It's very strange, right? It's 0 everywhere else, other than at one point it's infinity, but the integral is 1. So if you have a finite difference method, you have only finite and many point values. It's very hard to describe a data function, right? Because if the grid point misses that point, the support of the data function, then the exact solution should be 0 at all these grid points. So typical way of doing things would be the following. People usually do a so-called modification, which is to convolute the data function with a kernel, like approximate Gaussian, for example, approximate data function. So you smear the data function into a wider stencil, then you can deal with it in the usual way. You can read it at grid points, and you can do other things. But this process of modification leads to large numerical errors. You can think about it physically, this is a very sharp thing, but then you smear it by this modification, which made it computationally feasible, but also introduces a lot of errors. However, the DG method is a good method because it's based on weak formulations, it's based on integrals. And you want to say that if I have a data function, if I multiply it by a test function, which is in my finite element space, which is piecewise polynomial, does this integral make sense? Actually, it does. So mathematicians have already shown that this is well-defined. So if you have a data function multiplied by a piecewise smooth function and integrate, then this function is well-defined. This integral is well-defined. So that means for DG schemes, you do not have to do modification. You can directly apply your original scheme to either the initial condition or the right-hand side or the solution itself containing data singularities. You can just use the good old method. So from a practical point of view, there's no change, right? You can just go ahead and use your original code to compute. The question is, actually, there are several questions. One is, what you have computed, is it accurate? Is it useful? Right? Is it close to the exact solution of the PDE? 2, would you have oscillations? Yes, you will have oscillations. Would these oscillations generate unphysical values, for example, negative density, that would make the system blow up? Actually, yes. The answer is later we will see examples that would cause difficulties. So even though the code can work, artificially, you can say that the code can be implemented just to solve this problem. You may still encounter a lot of difficulties and unanswered questions that should be addressed. So let's look at these issues one by one. For example, let's look at the simplest case. We have a linear conservation law, ut plus beta, which is a constant, ux equals 0, and the data function is in the initial condition. So this is a very simple case. So what would happen if you apply DG method to this problem? As I mentioned before, you can just apply the good old DG method to it with no modification. No modification is needed, even though U0x is not in L2. Data function is not in L2, but that's not important because what you need is you have a projection of data function into your computational space VH. This projection is well-defined because the integral of data function against piecewise polynomials, this integral is well-defined. So the L2 projection is well-defined. So you can just go and compute. And moreover, it's very nice to know that what you have computed, U numerical, is in some sense a good approximation to the exact solution of the PDE here, even though the exact solution is lousy, right? The exact solution actually contains data singularities. So in strong convergence, you cannot say much, but in weak convergence, for example, at final time t, ut minus uht, ut is the exact solution of the PDE, uht is the DG solution. If you measure this in negative norm, negative Sobolev norm, which is defined by integrals, then you can actually have high order. So if you use piecewise polynomial of degree k, your convergence rate is h to the power k or k plus half, depending on what order of the negative. So depending on different norms you take on the arrow. So either way, you can see that this is indeed a high order method, right? Because u minus uh is going down to 0 as h to the power k, which increases with the polynomial degree. You have to measure it in negative norm. But with this knowledge, what we could do is that we could do a post-processing of the numerical solution. Then you would be able to recover in strong norm. So this will be the strong norm, L2 norm, but in a region away from the support of the data singularity. So this is the story. If you have a numerical solution, your exact solution, if you want to measure the exact solution minus the numerical solution in a weak norm, then you don't have to exclude anything. This weak norm is defined everywhere. You will have high order accuracy in this weak norm. If, on the other hand, you want a strong norm, you want u to be very strongly close to uh very strongly close to u, then you have to first, you have to do post-processing, and second, you have to measure the error away from the data singularity. Very reasonable, right? Near the data singularity, of course, you cannot expect anything in the strong norm. So this is a mathematically provable thing. It indicates that the DG method not only is usable with no modification to the to solve problems with data singularities, but also is indeed high order accurate, at least in this sense. Of course, this is a simple case, linear, right? Several comments. So this is how the proof. So I will not mention the proof, but it uses the techniques in another paper. Also, the negative norm business follows the framework of this early work of Cockburn, Laskin, Sully, and myself. By the way, I would like to mention that this negative norm thing is actually a very good framework for handling high-order methods to compute not so regular solutions. If it's a smooth solution, maybe it's not necessary to talk about the negative norm. You can just prove convergence in strong norms. But if your solution is very lousy, like in this case, it has a data singularity, then you cannot expect the numerical method to converge to the numerical solution, converge to the exact solution in strong norms to high order. You are asking too much. However, in negative norms, you could still ask that, and sometimes you can get it, like in this case. Okay, so this is a numerical example. You can see that indeed, after post-processing, P1 polynomial you get third order, P2 fifth order, P3 seventh order. So this is 2k plus 1, right, after post-processing, and measure it away from the singularity. Okay, 2 dimensions, you can get the same thing. Q1, third order, Q2, fifth order. Okay, you can do systems, hyperbolic systems, get the same thing. So this is the picture of what you compute. This is the numerical data function. You can see that it's oscillatory, right? It's oscillatory here around the data singularity. So this is the approximation to data function by a piecewise polynomial function. This is a good approximation because we have proved that in negative norm, this function is very close to the original solution, which is a data function. Okay, you can do the same thing for source terms. Basically, the idea is to use Duhamel's principle to, if you know how to deal with the initial condition, you can also deal with the source term because you can convert source terms to the initial condition using the Duhamel's principle. Okay, now let me come to this issue, high order accurate bound preserving limiter. As I mentioned before, so this method does the following. It basically computes a piecewise polynomial, right, which approximates your exact solution. What you can expect is that this piecewise polynomial function UH is very close to an exact solution U in a weak sense, because it's measured in negative norm, measured in integrals, measured in moments. If you look at the point-wise, they are not so close, especially near the data singularity. The numerical solution is going to be oscillatory there. This poses the following problem. If your problem is physically driven, that is valid only for a certain range of the solution U. For example, U is density, so it should be positive. So then this particular method would compute the negative density. So you might say, well, what's the big deal? Compute negative density. You just keep the negative density, knowing that this is a numerical error. This is okay for the linear problem that I have shown before. However, it is not okay for some problems that I will later show, for example, pressureless Euler or another equation from Flocking. Over there, the PDE itself becomes ill-posed if U becomes negative. In other words, not only will you see negative densities which are unpleasant, but also it will cause the code to blow up because the PDE becomes ill-posed when you reach the negative density. And any numerical method solving an ill-posed PDE will blow up, right? I mean, there is no stable method for solving an ill-posed PDE. So this is more serious because if the code crashes, of course, you cannot say the method is good. So then you will really need a bound-preserving limiter. Roughly speaking, the bound-preserving limiter is a post-processing technique which applies to your numerical solution and makes it to go within the bound. However, it looks easy, right? You just push it back to the bound, but you cannot really brutally do that. The reason is that if you just push every negative thing up, what you will do is that you probably lose conservation, because all these densities, they should sum to 1, right? They should integrate to the original mass. If you just push something up without pushing something down, you will increase mass. So that's not good. Also, it will could lead to serious accuracy issue. So if you push it up, maybe even in smooth regions, there could be some negative values. You push it up, you may lose accuracy there. So either you lose conservation or lose accuracy. These are undesirable. Or you could also lead to, if it is a very strong limiter, it could also lead to a deterioration of your numerical resolution. So your numerical data function is very sharp, but if you apply a limiter, a very, very strong limiter, for example, it becomes almost a first-order scheme, then your solution will become very much smeared. And that's not desirable either. So there is an issue here, how you can design a good bound-preserving limiter which can be mathematically proven to be conservative and also keeps the high-order accuracy in smooth regions. So this is extremely useful in this context. Like I mentioned, if you use the usual limiters like muscle limiters or other limiters on data functions, they smear. The muscle limiter is a slope limiter. Basically, it says if the slope is too big, I flatten it. So this limiter is very, very popular in CFD, in computational fluid dynamics, for problems containing just discontinuities, shocks. So if you have overshoot, you cut it down so to avoid oscillations. But for data functions, because if you think about the data function, the slope is very high, right? It's almost vertical. So if you use slope limiters on it, you flatten it a lot, and that resolution, the resolution of data functions becomes severely affected if you apply the usual min-mod limiter. So that's not a good idea. You want to use a much milder, much weaker limiter, but still it has to do the job. So this is a work. It's an independent work done with Xiangxiong Zhang. By the way, I probably forgot to mention that, but their names were on the first page of the slides. So this joint work with 3 people. Is Yang, who is my former PhD student, now a faculty member at the Michigan Tech, and Xiangxiong Zhang, who is my former PhD student, now a faculty member at Purdue. And so this part, this limiter, was basically the thesis work of Xiangxiong. It's firstly done without considering data functions. We are just applying it to data functions. So this limiter is the following. The first, when it was designed, it was to enforce Mason principle. So basically, if you have the entropy solution to this PDE with this minimum and the maximum initially, then the entropy solution stays in the bound. So the idea is that you want to keep your numerical solution also to be in the bound. So how do you do that? Okay, first order scheme is very easily done. This is the first order scheme. It's a conservative scheme. Remember this, I used f hat before here as this monotone flux h, which remember is increasing in the first argument, decreasing in the second. So this is a 3-point first order scheme. So un plus 1j is computed through unj minus 1, unj and unj plus 1 through this formula. Why does it satisfy Maxwell's principle? Well, for first order scheme, it's very easy to see. If h is increasing in the first one and decreasing in the second, then capital H, for example, if you look at the capital H related to this argument, small h is increasing here. The coefficient here in front is positive. So capital H is increasing in this argument. Capital H is also increasing in this argument because this argument appears only here. Small h is decreasing in this argument. The coefficient in front is negative. So it's also increasing here. How about here? Well, the small uj appears at 3 different places. At these 2 places, they appear in the wrong way because h is increasing here, but there's a negative sign. H is decreasing here, but there's a positive sign. So if you take a partial derivative of capital H with respect to this argument, you get 1 minus lambda h sub 1 plus lambda h sub 2. H sub 2 means partial h, partial the second argument. So basically, it's 1 minus lambda times a positive number. So what it means is that if you take lambda to be small enough, less than some constant lambda 0, then y minus lambda times that quantity would be positive, as long as you take lambda to be smaller than 1 over the bound of that quantity. So this is why first order schemes are monotone. In other words, it's an increasing function of all 3 arguments, provided you satisfy a CFL condition. Remember, lambda is delta t over delta x, is the time step over spatial mesh size. Okay, so for first order scheme, you can see in this one slide that this property is true. The capital H is increasing in all arguments. Then Maxwell's principle is kind of trivial because you see, if you put the CCC in constant, then this is C. So if you have h lambda of these 3 guys, if each of them is bigger than small m, then since capital H is increasing in all 3, it is going to be bigger than or equal to capital H lambda of 3 small m's. But this is m by this equality. So this number you compute is bigger than or equal to small m. By the same token, it's smaller than or equal to capital M. So as long as the previous 3 numbers are between the lower bound and upper bound, your computed next step value is also in the same bound. So this is a trivial consequence. Maxwell's principle becomes a trivial consequence of monotonicity. Remember, monotonicity is used heavily, right? Both in PDE and in numerical analysis. So in PDE, a lot of proofs are based on monotonicity. So you can, this is all good news, but the bad news is that I already mentioned before, if you insist on using monotone schemes, then your scheme can be only first order accurate. Then it will be not so efficient, right? When you want resolution, you would need a lot of points. But you see this bound preserving for first order scheme is trivial. Then even for second order schemes, this is no longer trivial. Because if you use Lars-Wendorf scheme, which is second order, you can see that one of the coefficients becomes negative. And this is true regardless of how you choose the second order scheme or second or higher order scheme. One of the coefficients must be negative. This is the so-called Gordonov theorem. This is true if you pick a linear scheme, if your coefficient does not, each of the coefficients does not depend on you. So this is a linear scheme, then Gordonov theorem says that as long as you have at least second order accuracy, you cannot be monotone. One of the coefficients must be negative, then you cannot satisfy Maxwell's principle. Think about it, right? If this coefficient is negative, if all 3 numbers are positive, I just have to make these 2 numbers 0 and make this number positive. then this guy would become negative. So immediately, all three previous values are positive. The computed value at the next time step would become negative. And this is true regardless of how small you take lambda. So even for second-order schemes, this is an issue. For linear schemes, Godunov theorem. For nonlinear schemes, you can do better. So there are a lot of work in the 80s and the 90s. Actually started in the 70s of last century, in the 80s and 90s. So a lot of total variation diminishing schemes and also Eno schemes, Veno schemes, and so on. But these schemes have either failed, the strong Mason principle preserving property, like these schemes, they are not Mason principle preserving. You can see a small negative value even if the exact solution is positive. Or these schemes, they satisfy Mason principle, but they are not truly high-order accurate. They are high-order accurate in smooth monotone regions, like a sine function. Between the two extremes, it is high-order. But at the highest point, near the highest point and near the lowest point, the scheme degenerates to first-order accuracy. So you would have all these difficulties. So the idea is now we would want to have a Mason principle satisfying scheme which is truly high-order accurate, even at the extreme. It is possible. So this basically is possible if we put it in this way. We put it in this way. So if unx is less than small m and bigger than capital M, this is the assumption, then un plus 1x should also satisfy this for any x. Remember, this unx is my numerical solution. Finite element is a little bit different from finite difference. Your numerical solution itself is a function. It's not just a bunch of grid values. It's a piecewise polynomial. So it makes sense to say this piecewise polynomial as a function is between the lower bound and the upper bound for all x. So this is the assumption at time level n. Then this is what I need to achieve. Then I can move on, right? So if I can achieve this, then I can do one by one and can reach all the way to the top with the same bounds. So this is possible to do. Again, I summarize, right? Basically, you assume at time level n, you are in this bound. So cell average is also in the bound because if pointwise is in the bound, the integral is in the bound. Also, it is accurate. Un minus the exact solution is delta x to the power p. So this is my assumption. I want to have the same consequence at time level n plus 1. How do I do that? Well, I break this procedure into two stages, two steps. First, I require my cell average at the next time step to be in the bound. This is the most difficult part. And the second, once the cell average is in the bound, I apply a limiter to make the whole function to be in the bound. And at the same time, I prove that the limiter does not kill accuracy, maintains this high-order accuracy. Okay, so this thing. So how do you make this into the bound? It's actually a simple idea, but it took us a lot of time to realize that. The previous work used the following way. It used the exact solution. You see, the thing is that if you use the exact solution does satisfy Mason principle. So if you can implement the exact solution for short time, then certainly your computed cell average will be okay, will be half. But this has a lot of limitations. This has been done in many papers. But this has a lot of limitation because it's very hard to generalize this to 2D and to systems. Because over there, it's almost impossible, even for small time, even if the initial condition is piecewise polynomial. It's almost impossible to implement the exact solution solver. But if you can do that, then of course, you get the Mason principle. If you don't do that, use longitudinal multi-step, then usually you get something which goes beyond the bound. So let's look at our way of how do we use these guys and still get the cell average into the bound. Let's look at the evolution of the cell average for a DG scheme. notice that this scheme, this evolution formula, is very similar to the first order scheme. The only difference is that this is cell average, but these guys are the polynomial values at the cell interface. Like j minus half, you have one polynomial on the left, which has a value, u of j minus half minus. And also you have one value on the right, which gives you a value, u of j minus half plus. So you have these 5 numbers. The cell average, the function value at the right boundary, 2 values, because it's a discontinuous guy. And the function value on the left, also 2 values, because it's discontinuous. So this cell average is computed by 5 guys. It's a function of 5 guys. If I mimic what I did for first order scheme, I would hope that this capital G is an increasing function of all 5. Then I'm all set, because I would just require all 5 guys to be between small m and capital M. Then I would automatically get this guy to be in small m and capital M. Right? However, you can easily check that you're not so lucky. Capital G is increasing in these 3 guys, but decreasing in these blue guys. So these blue guys are causing trouble. And also, this indicates that you can easily build a counterexample such that all 5 numbers are in the bound, are positive, for example, but the computed guy here is negative. Because you just have to deal with this wrong-going guy, right? Make the other upgoing guys to be 0, for example, the wrong-going guys to be positive, then you just get a negative number. So this indicates that it's not enough to require that your polynomial at time level n to have a cell average and the boundary values to be in the bound. It's probably necessary, but it's not sufficient, because you can see this wrong dependency on these 2 values. So what do you do with this? Well, the trick is that you notice that these 2 bad guys are the left boundary, it is the right limit. On the right boundary, it is the left limit. So it's basically the cell I. So there's a cell ij here. I have a polynomial here in this cell. Basically, the 2 bad guys are the 2 values on the boundary of this polynomial. And the good guy, the cell average, this guy, which is very good, is the cell average of the same polynomial. So these 2 bad guys and this good guy are closely related. They come from the same polynomial. So the idea is you want this good guy to help these 2 bad guys. So that's a very simple idea. How? You have to relate them. Basically, if you want A to help B and C, you better form a group and put them together. Then A would be able to help B and C. So in other words, I would have to write this cell average in terms of this and something else. How do you do that? Well, you can easily see that that's easy, because cell average is just an integral. It's an integration of a polynomial. An integration of a polynomial can be written exactly as a quadrature, as a summation of the polynomial at certain points times weights. Is that right? This is you learn from elementary numerical analysis. So yeah, so this is what you do. You just use this quadrature. Gauss is called Gauss-Lobato quadrature, which means you pick some values, including the boundary, and maybe some middle guy, 1/√3 or whatever. Then you can write down the cell average to be exactly, this is not an approximation, this is an equality that's important. Because if you have a polynomial of degree, let's say 3, then you can use Simpson's rule. Is that right? Well, anyway, you can use enough quadrature points to compute your polynomial exactly with no error. So you get the cell average is just this identity. Once you have this, you replace the cell average by this identity, then you add and subtract the term. At the end of the day, you rewrite u bar n plus 1 into a sum of 3 things. The first thing is a first order operator, capital H, with a modified lambda over omega m. Omega are these Gauss quadrature weights. evaluating at these three guys. This is also the first order operator evaluating at these three guys, and plus some of these polynomials evaluated at some middle quadrature points. Okay, now it becomes very easy because I know that this first order operator, as long as this guy, this lambda over omega m is less than or equal to lambda 0, as long as these three guys are positive, then this whole thing is positive, right? As long as these three guys are in small m and capital M, then the result is in small m and capital M. Similarly here. And if I require also that the polynomial at these middle points are between small m and capital M, then it is just a convex combination, because all these omegas sum to 1. These are quadrature weights. It's a convex combination of a bunch of guys. Each one of them is positive, or each one of them is between 0 and 1. Then certainly the convex combination is between 0 and 1. So you immediately see that the cell average falls into your desired bound. The only condition you need is that at these quadrature points, here, there will be 4 of them. These 4 guys would have to be in the bound. And also, you need a modified CFL condition. You need this CFL condition to be lambda over omega m is less than lambda 0. It's more severe than the first order condition, which is lambda less than lambda 0. Lambda over omega m, depending on what quadrature you use. Simpson's rule, omega m is 1 over 6. So this time, your time step is reduced 6-fold. So that's the price you pay. But once you have this, then you immediately, once you have this, immediately have the cell average falling into your desired bound. So this is the most important ingredient. Once you have this, then you can put the polynomial itself into the bound. So the idea is that first you require that the cell average goes into your desired bound. This is the most important because you cannot touch cell average. A conservative scheme, if you touch cell average, you affect conservation. But if cell average is already in the bound, the polynomial itself goes out, then I can simply squeeze the polynomial. This is the limiter. See, if the polynomial pj is not behaving, I subtract u bar j from it, subtract the cell average, plus the cell average is still pj, and I multiply it by theta, multiply this part by theta. In other words, you have a polynomial, you subtract the cell average, and then you squeeze the remaining result towards the cell average. You squeeze it by a factor theta. Theta is computed here. You can see that the formula depends only on the evaluation of the original unlimited polynomial at this quadrature point. So you only have to compute these 4 circled guys. And then you can compute theta. Then you can easily compute the limited polynomial p delta j. So this procedure is extremely efficient, right? It's a local limiter, doesn't even talk to neighbors. You just compute the limiting inside your cell. You compute your original polynomial unlimited at certain points. Then you compute the theta. Then you limit the polynomial by this theta. That's all you do. So the whole thing you add on top of your original DG is this thing, this very small limiter. So what does this limiter do? First, it guarantees that at the quadrature points, it will become positive or in the bound. Then the next cell average will be in the bound. Second, most importantly, there is this lemma. It says that what you have done have not affected accuracy. Because you might wonder, right? I compute this theta. If theta is less than 1, let's say if theta is 1/2, then I really changed the original polynomial a lot, right? Does it affect accuracy? The original polynomial is high order accurate, high order close to my exact solution. So if I perform this limiter, it is still high order accurate to the original function. It's highly non-trivial. It's not clear, right? But you can prove mathematically that this is indeed the case. So this limiter does not kill accuracy. It's very different from muscle limiter or other limiters, which will kill accuracy at the smooth extrema. This one doesn't. So it's a limiter which is very easy to compute, very local, cost is very small, does the job which enforces Mason principle, but it does not kill accuracy. So this limiter is the one which we modify to the system case. You can generalize this to systems, to 2D and so on, because it's based on quadratures. So as long as you can compute the quadrature, even if there's a triangle or whatever, if you can compute the integral of a polynomial on that object by summation of certain point values with positive weights, then you are in good shape. So this you can do in many, I mean, triangles or tetrahedrons, anything you can do. So this is going to be easy to be generalized to 2D and systems which have been done, and to different PDEs. So we are basically applying or generalizing this technique to positivity preserving for systems. Here I will skip, but the idea is basically the same. It will be becoming a little bit different because it's another scalar equation. So the quantity you want to force positivity may not be one of the original variables. For example, you want to enforce pressure to be positive, but pressure is not one of these variables of U. Then what you need is the following. You would need, first of all, you need a first order scheme which behaves. Just like the monotone scheme. Remember, I started with a monotone scheme. I showed that the monotone scheme is maximum principle satisfying. But for systems, there is no monotone scheme. So you would have to start with something in the system, Gordonov scheme, Lars Fridges, kinetic, and so on. And then you would then use one of these schemes to show that it is positivity preserving. Once this is true, then the quantity you want to enforce maximum principle or positivity must be a concave function of the conserved variable. Must be either one of the components like density or a concave function. In other words, the second derivative must be negative definite. Then in this case, you can show by convexity, you can show that the same trick that you used for the scalar case would work for systems. So this is what we have done. Then let's look at some applications very quickly. We'll be done. So this PDE, it looks like a conservation law, but this fx is actually globally defined. This fx involves integral. This PDE has a very strange property that if you put a smooth initial condition, it becomes a bunch of data functions later. It actually, so it won't happen for general conservation laws because there's a maximum principle. If you put the initial condition between 0 and 1, it will stay between 0 and 1. But for this one, this is not a conservation law, right? Because the flux is global. It actually happens that it spontaneously generates data functions. And also, if you compute a negative thing, if you compute a negative density for this case, the code immediately blows up because the PDE is ill-posed for negative density. So this one, with this bound preserving limiter, we can then compute it with P1 polynomials. And we have better, these are data functions. We have a better result than P0, because constant, because they are taller. The reason is that the integral underneath these curves are constants, so this is the mass. So the taller the data functions, the narrower, right, the resolution. So that means you are getting better resolution to data functions. You can do 2D. You get these kind of data functions very nicely. And another example is the pressureless Euler. Also, this is the example that you can compute, you can put bounded initial condition, data function will be spontaneously generated from the solution. So then you use the bound preserving limiter. You see it generates a data function in 1D. You can generate a data function in 2D. Also, this kind of codimension 1 data function, codimension 2 data function. So you can have all these things. The code can handle and compute them very well. This is a data function around the ring with vacuum basically inside, and so on. So basically the concluding remarks is that you have this method called the Discontinuous GAlerkin method, which belongs to finite elements in the integral sense. It can be used very effectively to solve conservation laws. It has, even for problems with data singularities, you can say something both theoretically and numerically. Theoretically, at least you can say that for simple linear PDEs, you have actually high order convergence, but you have to measure it in negative norm. For nonlinear case, you want a bound preserving limiter. So it's important to design, apply a bound preserving limiter. Together with DG, with the bound preserving limiter, you can compute the problem with data singularities in a very nice way. Okay, so with this, I finished my talk, and I thank you for your attention.
Question? Thank you very much.
Okay.